Yeah, it's recording. I think. Yes. Okay, great.
Said it was.
Okay, welcome to week 8 of the Agda reading group. This week we're going to talk about universals and existentials. Exciting stuff. So, as they say, we have seen universal quantifiers before, which is typed using the for all symbol, which is /for all. I think the word for all also possibly works, maybe.
I'm not sure.
Maybe not. Anyway, the usual.
I think so. I think I tried that once.
You tried that once, it did. Okay. Yes. So it's for those in, yeah. It introduces new variables in scope at the type level, and then you can use them in the right-hand side of your type. And yes, introduces them as standard arguments as well, so you can pattern match on them in the same way. Yeah. Yes, even though yes, what I'm trying to say is that even though the right-hand side of this is not a value, but it's a type, it doesn't change the fact that you're just introducing these as arguments, and therefore you pattern match on them. Obviously, these are when you're using universal quantification and you're giving names to them, then it's implicitly a dependent type, because if you're giving names to them, that implies you're going to use them on the right hand side, and therefore the type that you're writing.
So one thing in Agda is for all, you can do without a for all altogether. You can write the same thing here without ever typing a for all, because this is basically just a function, and this is the feature of of the fact that we're it's a dependent type theory, and so the universal quantification is just a dependent function. So it's not really.
Yes, so for all isn't.
It's not
meaningful.
A first order universal quantifier in any sort of first order logic sense. It's a dependent function space. So what the for all does in reality in Agda is it allows you not to give types explicitly to your argument. So if you would, Matthew, if I could ask you to, propositional equality.
I opened an issue on the standard library and it got shot to change this to equality.propositional, and it got
propositional.
Typo.
Typo, thank you.
Yeah, so first thing is we can, we can kill the for all. So why would we type the for all?
Well.
And if you add the for all back in and kill the type. So it tells Agda these guys are just, in a sense, these are not types, these are variables, infer the type for me.
So this doesn't work. So you have to have either the types or the.
Yes.
Okay.
Because otherwise it treats this as a type, and it doesn't know of the type called lowercase m, right? And yeah, it doesn't make sense.
In general, the standard library style is to usually write the for all always.
It's easier to read.
Just because it's easier to read. Semantically, it makes a lot more. A user reading it is.
But in a way, it is. It's built in, and it's not really.
It's not adding anything to the underlying theory.
Yeah, and it's it's the dependent type theory thing about merging the function space with the universal quantification, I suppose, on some level.
Yeah, that's really helpful actually.
So Yes, as Philippa said, it's really just a function, dependent type function beneath, and therefore something of that type is
Is a lambda.
a lambda
right?
that takes in.
So it's a very fancy function type, so it's a very fancy function. That's the witness for this type.
Yes, and you can eliminate it by providing, I mean, it's a function, so it works for all arguments. If you want to prove something about an individual set of arguments, well, you just apply the function and it gives you, you can eliminate it by applying the function.
Yeah, so really implication is just in Agda, implication is just a very narrowed down universal quantifier, right? An independent universal quantifier, and a universal quantifier where you don't care about the name, which sort of muddles the waters a little bit if you think in terms of first order logic, because these things come from different units.
Can I ask you a question?
Yes.
Would you ever have a reason for using this for all elim function that you're defining because it's just applying L to M?
I have never used anything like it.
No, you generally just apply the for all.
Yeah.
Would there ever be any point in defining that?
I think it's basically an illustration, right? That something that resembles your usual elimination rule for universal quantifiers if you squint a bit. Because, you know, if you're thinking first order logic, then it sort of resembles the first order logic rule, but not quite.
So there's nothing other than a didactic pedagogical reason for showing this?
I think so, yes.
Okay, thank you. I was just worried that there might actually arise some cases where it would help.
I
don't think.
Struggling to think, even in terms of, so occasionally you define very obvious looking functions like this to help Agda with inference. But I am struggling to think of any scenario where it would help in this case.
I don't think.
I don't think, because it's got all the information it needs when you apply L to M.
Yeah.
So I don't think, no, I can't think of any.
No, basically, if you apply, then the L has to be a for all, right? The L has to be a function, so it has to be what we would think about as a universal quantifier or dependent function. So I'm not in this case. Sometimes it's also a question of binding, like with the begin thing. But again, this is just a function name, so no precedence issues either.
Thank you.
Yes, and they're saying that these dependent functions can also be seen as dependent products. This notation is available in the standard library if you prefer it.
I was going to ask why that notation wasn't the one that was used, but now I know.
Yeah. Yes, I mean this is a notation that is used in Agda proper. This is some syntax defined additionally for those who want to use this style. So yes, I guess that the book goes with standard Agda. Why use the notation promoted by Agda itself. Okay, so this exercise is saying that if you have products of dependent types, then you can distribute for all over them. I don't have the definition of this loaded in my Agda environment easily. We'd have to go find it. So
you could show implications of both groups.
Yeah. Yes. Yeah. maybe we should do for all because that doesn't involve the.
Yeah.
So that. Okay, so we want to show that if we have a dependent function from x to bx or a dependent function from x to cx, we have a dependent function from x to bx or cx. I mean, this is hopefully it's not rocket science. A or b, and then so these arguments are implicit, right? If you remember with the curly braces, so they are automatically inferred by Agda.
Can you show the goal?
Can I show the
goal?
The goal.
Yeah.
Yeah.
Right. So it says they are implicit because and so you can't use them because they are not in scope. You've not named them explicitly.
But again,
Yeah.
you can
Yeah.
name
You
them.
can.
Just quick recap. You can name them, and then it would say they were in scope. Yeah. So we can pattern match on a. Should have given this a better name. B, and we can say, well, it's either have B or C. Inject one is the left injection, so we then need what are we?
That's
What's our
not
goal?
a B. That's an AR. Right?
Sorry, sure. Is that gonna work? So we now need to produce a function from x to bx or cx. We have two options. We can either have a lambda on the right hand side, or we can add it as an argument x, an argument on the left hand side. Probably need to add it on the left hand side. Easier to pattern match on it, not that we need to, but in general. So we now need to produce a bx or cx. Well, that's easy enough. We can have a B, A to B, and we have an A. So we can just ask Agda to fill it in automatically for us, and it will tell us. But yeah, we just have the left-hand side and the similarly on the right-hand side. Anything to be said about the dependent functions here? Is anything being done differently from when we internally in Agda from when we had the non-dependent case?
I think this is the interesting bit, right? Nothing differs at all,
Yes.
except for the types. It's precisely like term-wise, it's the same problem. On the level of terms, this is the same proof that we had when this was an implication. And the only thing that differs is that the results can depend on the x, right? And this is the definition between implication and universal in that theory.
Yeah. Yes, define a type with 3 elements, a set with 3 elements, and then they want to show this isomorphic between a product of a dependent function from trie to B is isomorphic from to the product. And yeah, that's it for universals. So
I think the important thing about universals is we've been using them all along, sort of.
okay, existential. Existentials are slightly different. I mean, they're not. You don't have native syntax for them in Agda built in. They're really well, data types or record types give you the facility to define an existential. So here they are giving one in terms of data type. So it's a dependent data type. It's saying, okay, we have something of, it's parameterized by 2 types, A, which is the witness, and B, which is what the property, which is a function from a witness to another type, and that's a property you want to hold of your witness to the existential. And how do you construct it? Well, you provide a witness of type A, and then you provide a proof that B holds of that element of type A, and therefore you prove that there exists something. There exists something of type A such that property B holds. And yes, this is really just a dependent. We defined pairs, non-dependent pairs earlier, I think. A times B. This is a dependent pair. This is a pair where the second element, the type of the second element depends on what you've got in the first element. Syntax declarations. Ooh. This is a feature of Agda that I've never really grokked. I've never really got my head around exactly what's a valid syntax declarations and what aren't valid syntax declarations, and the difference between pattern synonyms and syntax declarations. Okay. Don't look at you. Okay. I was so hopeful that you're going to come up with a clear explanation.
No, I can barely use that thing.
Yeah, okay. Okay, which maybe goes to show that maybe this area of Agda this particular feature of Agda is not super usable. I don't know. So
the point is the pair constructor is more intuitive for non-dependent pairs, right? For products.
Yeah.
And they want to provide us with slightly better syntax. And they do. And it's just some sorts of syntactic extension that we can use in order to write the sigma types that sort of match up with the pi types that we've seen earlier.
Yeah, so I think the crucial thing to say about syntax is that it can be used to introduce new forms of binders, right? So it can be used to bind new variables. So this actually introduces X in scope, this notation. If you say sigma X of type A, then anything after this part of the syntax, X is actually in scope. And they've done that by saying that it's syntax really for a lambda function. It translates to this, translates to that. And yeah, this just provides, yeah.
Yeah, I think, yeah, the right-hand side translates to the left-hand side because reasons, and yeah. That's a slightly nicer syntax.
So again, if you want to prove a dependent product, then you just use the constructor. And
So the weird thing about that is that on the left, there's no connection between X and A, right? I mean, why would X have anything to do with A?
Because there is no connection between X and A, not really. It's sort of because of the type of sigma, it expects a dependent function from A to Z as its second argument, right?
Right.
And so, you know, because it's a dependent function from A to Z, X has to be of type A.
Yeah.
This is the connection, but
yeah. Okay. So we've already defined sigma, and now.
Yeah, and it goes through the sigma. So.
Yeah. Okay.
I'm always confused about why it doesn't have a B of X or something somewhere. I mean, B in this.
It's open.
It's open, yeah.
Yeah.
I find that confusing too.
Yeah, I find this term is particularly baffling because lam X to B.
It's not a constant function. This is the problem, right?
Yeah.
Yeah. I mean, syntax extensions, syntax declarations. Like if you compare it to notation mechanism of Coq, it's not less understandable. I don't think so.
Yeah,
It's
golf notations are also very confusing.
yes. So
Yeah. So yes, you can use this form. They're going to introduce a nicer form, but I always used to write existentials in a second. So,
yeah.
Which is more intuitive. Okay, so they're saying we define it as a data type, but as a one constructed data type, but equally we can define it as a record.
If I can just go back, one important practical thing about the syntax is that the square brackets are parts of the identifier. So you can't, you have to have a space between the square bracket and an X and the B and the square bracket. And I usually omit it, and then Agda is very confused, and then I am very confused, and yeah. Only parentheses, the normal parentheses, and maybe lambdas are special. Everything else requires white space.
Yep.
Well, maybe curlies. Yeah. Anyway.
Okay, so yes, alternative way of defining it as a record with two fields. The first field was the witness, and the second field is it's be applied to the witness, so proof that the property holds for the witness. And you can,
So I think this is probably the first time we see a dependent record.
Yeah.
Maybe not, but at any rate, here it's quite possibly quite confusing because you have to use the field of the record to define the type of the following fields in the record.
Yeah.
Right. So yes, this is the dependency of the existential. Right?
These are, these are extremely useful because, you can define, for instance, if you want to define an algebraic structure, a semi-ring or whatever, or a semi-group, you can define the operator as one field, and then as the first field, and then you can define, okay, associativity. The operator also has to be associative, and the second field depends on the first field, and you can wrap everything to do with a semi-group up into a single record. Can construct it because they haven't given. You have to construct it using the record syntax because they haven't given a nice constructor for the record. And yes, it's provably isomorphic to the earlier the data type definition. Saying yes, they can also be viewed as dependent sums, just as universals were viewed as dependent products, which justifies the use of sigma in earlier. And then they introduced a nice actual existential notation. Tend to use, but they don't. Ooh. Oh, they use the existential brackets. Okay, they don't use the existential notation I use. Okay. They have.
They follow the convention of the Agda standard library from a couple of versions ago, I suppose.
Well, no, this syntax still exists in the Agda standard library. You can still use this. Right. It's just not. So, okay. So, yeah, so they then define and exists as simply a. So I use this and not the syntax. So they define exists as simply it takes in some implicit witness type, and it takes in a function from A to that set. So if you're using this exists thing, you can say.
All right. So you do exists lambda.
Yeah. So what I tend to write is not use once they've defined that exists. I say exists X such that P of X. Which,
and one thing you can't do is get rid of the like use the arrow, but without.
Yeah. So that would be, again, you have to produce a witness. I mean, with this x at x is zero record. The pair type in the standard library uses just a single comma.
Without the
square brackets, which allows you to chain them, right? So if you then have a product, if you have a product of A times B times C, then you can just write A comma B comma C rather than having to start nesting brackets. Okay, so yeah, and then they define some additional syntax on top of that, which so you don't have to write the lambda if you don't want to. So it's exists x such a b analogously. Yeah, so a syntax when you're importing and exporting these things, well, when you're importing these things from other modules, you can't import the syntax. The syntax comes along for free automatically when you import the basic definition, which it's defined in terms of, if that makes sense. So you can't, I mean, this is a new top level definition. You could give it a type, just as we have exists. To import the syntax, you import exists syntax, not the form on the right hand side of the syntax declaration.
Yeah, the form on the right hand side does not exist. It's not a.
No, well, it doesn't exist. That's the thing which caught me out when I was first learning Agda, that I was trying to import. Oh, right, I was trying to import. I was putting exists brackets and then some variation of underscore bracket underscore and trying to import things like that.
That's the problem, right? The binding structure is off.
Yes, yeah. It's completely off.
Previously non-determinate number of variables, like in Conc you can do something like exists like number of things dot so that you can
no, it doesn't. You can you tend to do it with an n-ary product. You take a function from an n-ary product.
So you have to hack it basically.
Well, hack it, or it's definable in the language, right? And you don't need extra language extensions to do it. I mean, it's but no, you can't do arbitrary numbers of variables. Syntax doesn't support that. There's various restrictions on syntax that the core Agda developers hate and have spent 2-3 years trying to extend as well, but I don't understand why they want. I never quite understand what the limitations are. It's something about multiple dependent, transitive dependent types or something in the syntax on the left. So multiple arguments that transitively depend on each other, and something goes wrong. But for most purposes, it works reasonably well. Elimination.
So this elimination could actually be useful potentially, as opposed to the universal elimination.
Yes, because it's doing something non-trivial. It's unpacking the pair. So you have a function that takes. It's a universal. So if you have a witness to b of x, then you can produce a c. And you take in an argument that gives you a witness to b of x, and you can produce a c. Well, you have a function and you unpack the pair, and you apply it to both the witness and the proof that it holds.
And of course, if we forget about all this complicated type nonsense and just look at the term level stuff, we can see that this is
carrying.
Yeah.
Ooh. Yeah.
Just carrying, given, again, right? If all these things are non-dependent, then you will get the usual type of carrying. But if you get things to be properly dependent, well, the types go like this.
Yeah.
One of the more strange places, for me at least, is the dependent function composition, which is the standard function composition in Agda standard library, which is, yes,
scary type.
A little bit scary type, yes.
but yeah, just to make completely explicit and overly gory detail, what Philip just said is, if you take out, so X is type A, so you imagine this is something of type A to a non-dependent B to C, so you put a function from A to B to C, and this is a pair of something of type A and something of type B, then you generate something of type C. So it is, that's how you would reclaim the carrying rule in the non-dependent. And then they're saying, yes, we can prove an isomorphism between these. They've shown how to do. I'm not quite sure why they're not using exists lim here, given that they've defined it for the two function, but they are using pattern matching lambdas in exactly the same way as, well, to replicate what they've done on the left-hand side, taking an F, taking a pair of X and Y and apply F to X, Y. The opposite way is fairly simple. You take in your function G from pairs, you take in your arguments X and Y and you pair them up and apply G. And then the inverse is, well, it's proposition equal in the right to left direction, and then from the left to right direction. Right to left direction, you have to use extensionality. Exercises, probably not going to do any of them. They're relatively mechanical. I mean, all these examples, Agda will pretty much guide. If you use case split, auto, then pretty much all of them are
refine, case split, refine.
Yeah.
Just goes.
Yeah. So here's an example. We're going to apply even and odd numbers. So they're okay. So this is interesting. They're doing mutual. They have not introduced mutual definitions, have they?
Apparently they have. It was a while ago. The relations chapter was a while ago, I think.
Okay. Did they really?
I don't
okay.
know.
Well, as a recap, well, this is an example where, okay, well, let's have a look what it says. We'll leave out the weird thing that they're declaring them. They seem to be declaring them twice, but they say you're even. Well, you're even when you're zero. Zero is even. And it says for any number n, if you're odd, then if n is odd, then the n plus 1 is even. The successor of n is even. And likewise for odd, if you're even, then the successor of n is, then your successor is also odd. So you'll notice that these are mutually dependent, these definitions are dependent. Even refers to odd, and the definition of odd refers to even. So if you define these as standard data types and you gave the type, you didn't have these duplicate definitions up here, but you just added the type directly, then you would get an error because Agda is saying, look, these definitions are, you can't define even first without having defined odd, and you can't define odd without having defined even. So there's various ways of introducing this mutual dependencies in Agda. And this is the main one that is currently favored, which is that you declare the types of your functions first, or your types of your data declarations first, and all of them up front. And then Agda will know that they're in scope for the future, when you actually come to define your mutually inductive data definitions. And then you can use odd, even though you haven't given the definition of it yet. It still knows that it's going to be in scope.
I think it's a really neat design for mutual recursion. I really like it.
The alternative is that you can nest it under a mutual block. Philip is wincing.
I was sort of under the impression that it was deprecated or deprecated-ish, or maybe just not encouraged.
Not encouraged. Okay. Yeah. Okay. Well, maybe we won't even discuss it then.
Yeah. I mean, I think this works reasonably well. Yeah. I think it's really designed, since you have to give the types anyway. Basically, you give the types of all the stuff that's mutually defined, and then you give the definition separately.
I mean, so interestingly, I mean, you can also separate, you're not forced to define a mutual, giving the types first, you're not forced to find something that's mutually inductive, Agda won't complain if it's not mutually inductive. So you can
declare everything.
You can
and then
declare
define
everything and then define everything if you wanted, and Agda wouldn't have any problems. I'm not sure why you do that, but it's possible. Maybe if you were defining an interface or something that you only wanted to show people the types. Yes. So okay, so let's load these in because this is actually kind of fun exercise. Oh, subjects, excellent. So we would like to show, they want us to show that if a number is even if it's only twice another number, and it's odd if it's 1 plus twice another number. So let's try and again, this is going to be a mutually inductive. These are going to be mutually inductive proofs as well. So the proofs are going to depend on each other as well. So again, we have to define the types of the functions in advance, so that Agda knows that they're both in scope, and we can define. So, what arguments do we have for even? Well, we're going to have a proof that this number n that we've come in is even, and you can see E is in scope even, so we can k-split on E.
Yeah, and that's my one complaint about the syntax. It
One.
unfolds it in the goals. So you can see in the goals, you don't get the nice syntax printed. You get the exists syntax.
Yes. So they're working on this issue it's the Agda implementators meeting this week, and they are working on this. They're trying to take the internal representation. They're trying to take the approach that a language called small TT does, and they're trying to take the approach where internally they store both the original term as the user has written it and the normalized form of the term, or a computation that returns the normalized form anyway. And therefore, if you had both those pieces of information, then the normalized form is obviously useful for internal type checking and everything, and the non-normalized form can be used in display. And indeed in meta variable solving, which makes it much shorter. Okay, so let's have a look at what our goal is. Well, it's saying that we need an m such that m times 2 is equals 0. I'm not even going to bother to k-split. I'm going to press auto, and it's going to say, well, 2 times 0 is equal to 0, and the proof is just record. So we then need to prove that m times there exists an m such that m times 2 is equal to suck n. So, well,
should be fine because n is odd, right?
Yes.
As we know down in our assumptions.
Yes. Well, so we need to take even suck. What does even suck take? It takes a proof that's that's a proof that n is odd. Yeah. So we can apply odd exists to generate a witness such that 1 plus m times 2 equals n. So the problem is, well, okay, let's just see what it gives us. So this is going to give us an m such that suck of m times 2 equals n. And we need to use both parts of this pair, right? We will need to use both the witness to generate the new witness, and we need to use the proof that comes with this, that suck of m times 2 equals n is equal to n. So there are various ways we could do this, right? We can we have the functions, we can project out the first component, and then we'd have to duplicate it and project out the second component and do something to the second component. That's not very nice because we're going to be calling the same function twice. So we want to preserve sharing. the way that they suggest doing it in the book is to then just pattern match on the result of odd exists using a with statement. So with statements introduce an extra argument on the right hand side of the function. Even exists, even, so and then some pattern here, which is the result of the odd, which is the result of the thing that we're withing on, and then we can pattern match on V. Gives us horrible names for it. What is V? Well, the first one is our M, and the second one is our proof that 1 plus 2 times M is equal to suck M, or 1 plus N. So that allows us to pattern match on the result, and then we can use these
To N, not to suck M.
Yeah, sorry, to end.
Your name
Yeah.
doesn't match your time.
Yeah, sorry, yeah. 1 times 2, suck N. And then what do we need? We need a witness such that M times 2 is equal to suck N. Well, we have this now, right? Because we can now go suck M. And then we want to say 2 plus, I mean, it knows, so suck M is 2 times suck M was the original goal. It knows from a definition of multiplication, it knows that 2 times suck M is equal to suck M times 2. So it's normalized it to that. And we want it equal to suck N. We've got the inner bit is equal to N. So we just need to add a suck. We need to say that we need to take this proof that some value X equals Y, and we need to prove that X plus 1 equals Y plus 1, or 1 plus X equals 1 plus Y. And
Can it do it auto? Probably not.
pardon?
Can auto do it or?
No, it can't. Not unless you give it
Still
hints.
can't.
Well, no, it never applies. It never applies functions that are in scope unless you explicitly give it hints.
Okay.
So if you remember the congruence proof, this was the congruence proof, which this is just an instance of congruence proof that says if we have some function from A to B and we have 2 elements that are equal, then f of X is equal to f of Y. And in this case, the function is just plus 1 is suck. So and these brackets are highly irrelevant, but Agda likes inserting them. Okay, there are various ways that we can, let's do odd, yes. So odd, again, we're going to case split on our proof of oddness. We know it must be 1, even, and again, we can apply our even exists to get ooh, what did I type there? That was scary. M and 2 times M equals M. And then we need a witness, and again, it's just it's the same pattern. Oh, no, I've gone wrong.
It's just M.
Just M, yes. Okay, so mutually inductive functions, proofs, each one depends on the other. How can we make this slightly nicer to read? Well, the first thing is that I think we mentioned before, but the widths, you don't need to rewrite out all the existing arguments in the function, which is you can just do the ... and that implicitly duplicates all the previous pattern matching from function. This is useful when you obviously have a lot of arguments already introduced in scope. So let's do that. The next thing is that this is introducing some new free variable M So, and this is a proof of equality, right? It's saying that 1 plus 2 times n is equal to n. So we can actually pattern match on this proof if we wanted to. And we can pattern, we know the only thing that we can pattern match is REFL. And then because we pattern match on REFL, we forced that the new introduced argument is equal to suc of m times 2. The right-hand side just becomes REFL as well. Because by pattern matching on REFL on the left, we've forced Agda to unify n and suc of m times 2.
And of course it worked because one side of the equality was well, unifiable with the other. Right?
Yeah. Now there's some debate, right, about whether this is I mean, it's a shorter proof. You don't have to apply all these external functions. There's a reasonable argument that if you're going for clarity, this is a much clearer explanation of what's going on because you're not relying on the magic of the unifier.
That definitely tells you why it's equal rather than it's equal.
Yeah. Occasionally, sometimes the magic, the amount of effort saved by matching on REFL is so great. In this case, it's quite a simple proof. If it was a really deeply nested, if you weren't just applying some suc function and it wasn't just a simple congruence proof, then, and this thing, the magic of REFL sometimes makes it worth losing the readability just because it simplifies the proof so enormously that sometimes it's you give into the dark side and
Can I ask a question about that?
Pardon?
Can I ask a question about that?
Yeah.
The only reason why this is clearer is because you can pack a lot of information into your variable name.
Yes.
So wouldn't a comment with REFL be just the same?
Yes. Yeah, it would be.
So
I mean, well, it would be the same up to the point where if your proof, I mean, the comment is not checked by the type checker, right? Well,
the variable name is not either.
The variable, yes, you're absolutely right. Yeah, the variable name's not checked.
As a matter of fact, it's up to commutativity, your variable names, because of the way multiplication is defined.
Actually, well, it's not entirely true, right? Because it's not entirely the variable names, because there is this con suc, right? So you are knowing that you're having to apply the fact that 1 plus. You're applying the fact that one yeah.
But this is also the thing that you sometimes want to sweep under the rug because you really don't care after how many, like under what structure you're rewriting.
Yeah.
Thanks.
No, it's a great question, and you're absolutely right. I mean, the comments. I would highly encourage comments to Agda code. Very few people do it, but unless they're writing it for a paper. But if you'd like to buck the trend, then yeah. Yes, and make sure the proof.
So I suppose one more thing you can do in order to simplify is irrefutable pattern matches. I'm not sure.
Irrefutable pattern matches.
So yeah, you can do this in one line rather than two, because there's only one case, right? We are case splitting on the result of odd exists of O, but there's only one case.
So okay, so I have not used this syntax before, so let's try you. I think it's something like.
Yeah, you can get rid of the parents. So when there's just one case, magic. You can do it like so. And I mean, arguably it matches the sort of source and target of the thing you're using a little bit better.
Yeah. Yes. There we go. Yeah. So
this is what James wanted me to do last week in order to prettify my horrible Agda code in the seminar.
Yeah. yes, never use that, but yeah, I can see why that might be useful.
I think it's quite nice for. I mean, it's a trade-off, right? Sometimes, so you can break the lines, because one thing is the lines get very long. You can of course break the lines.
You can do
Both here
you
and
can do
here,
anything,
yeah.
any combination that you like.
I mean, I think it generally leads to something a little bit more readable.
Okay, then define the proof in the opposite direction, which is the same but simpler, because you don't have to pattern match on this intermediate, because you're returning because your proofs are only returning a single result that you don't have to deconstruct. Then you can just call the proofs directly instead of having to pattern match on the result in some manner. What? Hang on. What's the difference? Hang on, sorry, I'm going to be annoying and ask questions. So what's the difference between this?
Not sure there is.
I mean,
I'm not sure there is one.
That's much more readable.
Yes.
Okay.
I certainly find that much more readable.
Yeah, much more readable,
What?
because I see what's happening. The other one was very confusing, there were a lot of symbols.
So there must be some way in which irrefutable width is more powerful than a let.
Possibly.
But I'm not sure what
to
it
do
is.
with binding somehow, but how? But wait.
So okay, so yes.
Okay, yeah, that's something we should say.
Yeah.
When you were writing it, I was like, so my immediate was like,
Yeah.
okay, so Agda doesn't have a let.
Yeah, no, Agda.
Agda has several lets. There's also a where, and with where with a where clause, there's definitely some questions about bindings and scope. But
Yeah.
here I don't really see.
So okay, so another third. So lets have to be prepended in the actual body of a function. Wheres can come after. Wheres come after, so that you have less control about.
Also work, but
Yeah.
oh no, yeah, there's
Missing.
no time signature.
Oh, because I'm yeah.
You can only do this without the type signature.
Yeah.
Left hand side is a simple variable.
Yeah. Okay, so you can't use a where here.
Yeah.
Okay.
Yeah. So there's many ways, and some are nicer than others. Maybe the refutable lets would chain better if you used several assumptions in one go. Maybe, or maybe it's just a question of what you find.
Something to ask James.
Yeah.
Yes. Proving the other direction is a little bit conceptually simpler because there's no intermediate pattern matching. Notice that they are matching on REFL on the proofs of equality here to simplify things. You could equally do it with I think you'd have to do it with the inverse. Instead of saying congruence of suck, you'd have to prove that suck was injective.
Yes, injective.
You'd have to prove injectivity of suck, that you could strip off a suck constructor, which is slightly more. I mean, that actually.
And then the REFL actually is.
Then maybe the REFL helps, because you'd have to rely on another external, specifically built function to prove that you could remove a suck. Yes, and there's oh, we have not got to the end. I was thinking we got there. Okay, so negations. It's a constructive logic, so negation interacts with existentials and flaws in exactly the way that you would expect in a constructive logic. So not exists becomes for all not.
But the other direction.
But
like
not
the
for
other
all.
ones.
Not for all. You can't. If you've got a proof that not that for every element, that not. If you've got a proof of not for all, that you can't produce a proof of exists because there's no way to magic up a witness. May have proof of it now.
The other one probably.
Yeah. And then they want you to show an isomorphism between binary numbers and natural numbers, which is incredibly painful, and I would not recommend that you do because it is.
Really? I mean, I think it's a decent exercise. If you
It's-
actually want to code a little bit about that.
Okay.
Yeah.
Yes, okay. I maybe I'm colored by the standard libraries pain with binary representations of numbers. And then yes, it says where you get to in the standard library. So, any remaining questions about quantifiers and existentials? No? Okay.
If one wants to use the classical logic, what do we need to do?
If one wants,
Probably postulate something.
so, well,
Means there's some kind of import from standard library.
yeah, so there's what there is in the standard library, there is a axiom top level directory, source axiom, and there's various axioms. You could either postulate, so for instance, you could postulate something of type excluded middle. That is possibly unpleasant because when you postulated it, you have to mark everything as unsafe because you're going to introduce a postulate. A nicer way of doing it is to parameterize your module by excluded middle and say, if I have a proof of excluded middle. So the difference between, so you could go, axiom excluded middle. Oh yeah, okay, it doesn't like the same with this. Oh yeah. Okay, and then you would say excluded middle, and then you would then add it as a module parameter. You could then use excluded middle anywhere in your file, but you don't have to mark it as unsafe because the difference between postulate is saying that I do have excluded middle. This says if I had excluded middle, then I could prove this, which is safe, which is perfectly safe in Agda. So this is usually probably a better way of doing it if you want to maintain the guarantees that you're not. If you're writing a paper that uses excluded middle, then I would recommend using this approach rather than.
It's also probably even more unpleasant than using classical logic in Python.
No, the classical logic is very pleasant. I always do it. I'm incapable of doing otherwise. I cannot think if I don't have classical logic.
Yeah. No, but the thing is, here you're constructing programs, and like explicitly using excluded middle tends to be a little bit annoying.
Yeah, which is when I don't think I will ever be in position to actually practically use it. But it's good to see how things work.
Yes.
Cool.
Okay.
Hope everyone has a good week. Yeah. Thank you for coming. Well, I'll stick the recording up on YouTube at some point.
Thank you.
Thank you.